Yeah, I hope you can see my slide. Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you very much. Okay, so good morning again to all of you. And so what I'm going to do today, I'm going to first briefly talk about the plan, my plan for rest of the semester, the topics that I'm going to cover, and then I will start talking about the topic that I'm going to teach today. So briefly, this is something I'm going to talk about in this semester. So at least, I mean, for this lecture and next maybe couple of lectures, I'm going to focus on unsupervised learning, in particular flat clustering, graph clustering, principal component analysis and all. Then I'm going to spend some time, in fact, substantial amount of time on deep neural network. There I will focus on the feed-forward neural network, CNN, RNN, attention network, and some of their applications. Okay. And I would also like to tell you what is happening around in this particular area, the current trends and the challenges and so on and so forth. Okay. So I'm going to mainly focus on this particular thing in the next slide, few lectures. Then I'm going to focus on generative models like hidden Markov model, topic model in particular, latent Dirichlet allocation, and some other like tools that will be required to do the topic modeling stuff. Okay. And finally, I'm going to talk about few advanced topics, something like semi-supervised learning, online learning, adversarial learning, transfer learning, and positive on-demand learning. So depending upon the time that we have, I'm going to cover some of the things in detail. Okay. So maybe sometime in the November. So that's what the plan for rest of the semester. So today I'm going to particularly focusing on the unsupervised learning, and in particular I'm going to talk about two things, K-means and K-means plus. Okay, these are basically clustering techniques. Okay, and you get to know what is the main problem with the K-means and how K-means plus can solve the problem and so on. So you already, Professor Advait Mitra already gave you some introduction about unsupervised learning. Okay, I'm also adding a few things on top of this. So quickly, I just want to give you a couple of examples of unsupervised learning where these things can be applied and so on and so forth. And in this particular lecture, I'm primarily going to focus on the clustering stuff. Okay, so this is one such example where you want to do phase clustering, for instance, from videos. Okay, so you have a bunch of videos. And from these videos, you want to figure out who is who. Okay, you want to cluster the individuals. Okay, from a video. So what you typically do, like first of all, you have to identify the key frames, the frames which are basically conveying the useful information from the video. Then you run some kind of face detection algorithm to figure out that this is the face of an individual and so on. Then you do some feature engineering, okay, and followed by you basically use these features to cluster the faces. Okay, so that's what essentially the whole pipeline. So one of the component in this particular case is face clustering, where you want to apply clustering techniques. An interesting kind of application that often used in search engines, search result clustering. So objective is in this particular example, what you see is that your query is apples. Okay, so apple could mean many things. For example, apple could mean computer, the company Apple. The apple could mean, for example, the fruit apple, and so on and so forth. Now, nobody knows what you are looking for. So what the search engine will do, it will bring in few documents from web, and then it will cluster based on their content, so that you, in case you refer to this Apple as a company, okay, then you can get some document from the company. If in case you are thinking about fruit apple, then you also can get few documents from the fruit apple and so on and so forth. So that way it is done is that you bring some documents from the web, then you cluster based on the content, and then in top few kind of rank like 10, 20 and so on, you basically bring in documents from different clusters so that you represent everything possible. Okay. So this is typically the solution for ambiguous query. So when you are not very sure that what you are actually looking for. Now, another thing that like people use, like another application areas where clustering is heavily used is Google News. Okay. So for example, the Google News about the kind of the international stories, the politics, the sports, and so on and so forth. So typically what Google News, the system Google News does is that they essentially brings these documents and then cluster this document based on the content. Okay. So these are kind of few applications. There are wide ranges of applications that you can think of where clustering techniques are typically used. Okay, so what are the primary questions in clustering? Okay, so if you look at this particular data set, okay, so the points are essentially the individual points on some dimension. Okay, now clearly you can see there are three possible clusters. Okay, roughly. Okay, it is not always possible to visualize the clusters when you are dealing with very high dimensional data. So you have to apply some different techniques for that. But for the time being, say this is the cluster that you have. Okay, if you plot the whole thing. Now there are two primary problems in this case. Okay, first of all, you have to figure out what are the issues for clustering, the different issues that you have to figure out. Okay, and then you can figure out what kind of clustering algorithms that you have to use in order to solve this particular problem given a particular data. So depending upon the nature of the data, for instance, whether you have the feature vector data on some n-dimensional data, for example, whether you have graph data and so on and so forth. So depending upon the nature of the data, you have to figure out what kind of clustering algorithm you are going to use. Okay, and I'm going to cover in this next couple of lectures the different kinds of clustering algorithm on different types of data and so on. So before, this is common for all kinds of machine learning things, be supervised, unsupervised, and so on. So the first issue in clustering is that representation for clustering. Okay, so given the data, the raw data in particular, how do we represent the whole things? Okay, for example, when you're dealing with the video data, how do you represent this video data in a form that the clustering algorithms can actually handle? Okay, so it essentially calls the feature engineering. You extract some features out of the data, raw data, be it image, be it video, be it audio, or be it textual data and whatever, and so on and so forth. So you have to do feature engineering. And depending upon the nature of the data, you have to basically figure out what kind of feature engineering you want to apply. The second important thing in clustering, the similarity or the distance measure. Essentially, when you do clustering, you have to put together similar things. So you need to have some kind of similarity or distance measure, which will guide you that, okay, these 2 points are similar, so you can put them into same cluster and so on and so forth. Okay. So the next question, there are different types of clustering algorithm, whether you should apply flat clustering or hierarchical clustering. Okay. Then you have to figure out that how many clusters you really want to create. Okay, whether you can fix a priori, okay, that I want 10 clusters, 20 clusters, and so on, or whether you can actually use the data to figure out the good number of clusters. So these are some of the issues that we'll be discussing in this set of lectures when you will be applying different kinds of clustering techniques on different types of data. Now, broadly, if we classify the clustering algorithms, they fall under two different categories. One is called flat clustering, this is the hierarchical clustering. Okay. So in flat clustering, what happens is that typically the clusters are actually the mutually disjoint sets. Okay, something like that you can see in the top right. Okay, every point will belong to one particular cluster. They are mutually exclusive. There is no commonality between different clusters. And K-means clustering algorithm, which I'm going to talk about, is one such example. Okay. In hierarchical clustering, the clusters are typically overlapped. Okay. So it could be either bottom-up clustering, it could be either agglomerative top-down clustering, and so on and so forth. And you get to know when you will be doing on the graph data, primarily we will be dealing with the hierarchical clustering. Okay. The second issue is hard versus soft clustering. Okay. So in hard clustering, what happens is that each example belongs to exactly one cluster. You have a bunch of points and you want to group these points in such a way that one point will belong to exactly one cluster, no more than that. Okay. In case of soft clustering, an example can belong to more than one cluster, but with a membership value. Okay. There will be a membership value attached with each and every point in the data set. So for example, one point might belong to, say, for example, say category called, say, hockey with some membership, say, for example, 0.6. Another point can belong to, say, for another kind of sports. Okay, something like, say, for example, cricket. Okay, with, say, membership 0.3 and something like this. So it's basically probabilistic interpretation attached with this particular clustering techniques. Okay. So you cannot definitely say that one particular point will belong to this cluster, but you can say that this particular point, most likely this particular point will is conveying the information from this particular cluster and so on and so forth. Okay. So the first clustering algorithm that I'm going to talk about in this particular lecture is K-means clustering algorithm. Primarily because this is one of the most important clustering algorithm that people usually use. It's pretty simple, effective, efficient, and so on. I'll just give you kind of the broad steps of K-means, and then I will use kind of few examples to illustrate how it actually works. Okay. So K-means is pretty simple, both computationally as well as conceptually. Okay, and that's why people really, accepted it to use in many different kinds of application. So what are the main steps of K-means? The first step is that you have to initialize the cluster centroids. Okay, now your objective is that you have, say, a set of n points on some dimension, d-dimensional space. Okay, that means every point will have n d features. And so you have to basically group the whole thing, all the points into, say, k clusters. Clusters nothing but basically a group. So what you do, you start with k initial cluster centers. Okay, and I will talk about what are the different ways you can actually initialize these cluster centers. Okay, for the time being, that assume that you have to initialize this k cluster centers, which we call k-mean. Okay, next step would be to assign a cluster each member to the closest center. Now that you have different centers, now take each and every point from the data set, you find out the closest center and then put it into that particular cluster. So this is called the assignment step. Now, because you have grouped the different points, okay, on individual clusters, now that your cluster centroid actually changed. Okay, so you have to recalculate the centroids based on the assignments of these points. Okay, and then go back to step 2. So this step 2 and step 3 is basically an iterative steps. You repeatedly use these two things. Okay, again and again and again. So of course, because this is an iterative algorithm, you need to stop. So the stopping criterion could be, for example, you can like stop after fixed number of iteration, 10, 20, 30, whatever. Okay, or you could see that when the cluster, the individual points are not changing the cluster membership, they're not jumping from one cluster to another cluster, then we can say that your algorithm kind of stabilized on the data. So you can then stop. So there are broadly two different ways of basically, terminating your algorithm. Okay, and at the end of it, you are going to get two things. One, you are going to get k centroids. Each centroid will represent one particular cluster, and every point and their corresponding cluster membership. That point 1 belongs to cluster 3, point 2 belongs to cluster 5, and so on and so forth. Okay, so at the end of it, we are going to get something like this. Now, take a very simple example, which I will use to illustrate how K-means actually works. So assume that this is the whole set of points that you have, okay, and you want to clusters, okay? And so I say, for example, I want to create 3 clusters out of this data. That's what I want to do. Now, if you follow the steps, step 1, step 2, and step 3 of this clustering algorithm, so first step would be that you have to initialize the cluster centroids. For the time being, assume that I'm going to initialize the cluster centroid randomly. So I'm going to pick randomly 3 points from this data because I want to create 3 clusters. So these 3 colors basically represent the 3 different centroids. All right. Now my next step would be the step 2, where I'm going to assign or cluster each member to the closest center. Okay, I have to figure out the closest center for each of this point in the data set, and then basically I have to assign that point to that particular cluster. So now if you look at this whole thing, so color essentially I'm using this color to represent that, okay, how these points actually belong to individual clusters and so on and so forth. Okay, and if you do something like this based on the closest centroid, you're going to see that, okay, these different points are basically belonging to different clusters. Okay, now what happens if you look at this is that now your initial cluster centroids actually going to change. Okay, because it will depend on the points that you have in different clusters now. So what will happen? That if I compute the centroids means the kind of the middle point of all these points in individual clusters. So centroids will be somewhere near these three boxes. Okay, the blue, the red, and the purple. Okay, so three different positions you can get the centroids. So this is called the readjustment of the centers, which is basically step 3 in your algorithm. Okay, now because this is an iterative algorithm, so you're going to repeat the whole thing, the step 2 and step 3 again and again and again. So again, we have to go back to step 2. You again recompute the cluster assignments, okay, based on the closest centroid thing. You get something like this, okay. You can see the cluster memberships are changing. And after that, again, you have to apply step 3 to recalculate your centroids, okay, because now basically centroids, the different points of different memberships and so on and so forth. So step 2 and step 3 and so on. Now again, you have to go back to step 2. Okay, you do the things and same thing, reassignment of the cluster centroids and so on. And finally, you readjust again and so on. And in this way, you simply proceed. And finally, when you see that no changes are, basically there is no change in cluster memberships, that points are not changing from one center to one cluster to another cluster, you basically stop. Okay, so you can stop here, or you can basically stop after multiple number of iterations. The question is that when you will be dealing with very large volume of data, like billions and billions of points, then if you wait for no change termination, something like this, what I'm showing in this particular slide, then it's probably going to take lots of time. So people generally prefer termination after fixed number of iterations. That's perfectly all right, depending upon your computational resources, your time, and so on and so forth that you have. And so you can take one of these two policies that I have mentioned. Okay. Any question till now? Okay, all right. So this is kind of the broad, like this main, the algorithm of K-means clustering. Okay. Now, few things that we need to now fix. One is the, which I already mentioned, that you have to find out the closest center thing, okay, and then recalculate the centroid. So you simply take one particular point, find out the distances between the point and all other centroids in the cluster, okay, and then basically find out which is one the closest one. And that's the simple way I can do it. Here is a graphical example. So if you look at this particular example, what you can see that the point in the middle, the circle in the middle, will belong to the blue cluster, simply because the distance is actually minimum out of all the distances that you have here. Okay. Now the next is basically what distance measure one should use, because this distance measure is something which is going to tell you that how close a particular point is from a particular centroid. So one needs to figure out that what distance measure one would actually use. Okay. Now there are many kinds of distance measure, but the one that people generally use is Euclidean distance. It's just like, you know, you have n-dimensional vectors, and then you can simply take the Euclidean distance. Okay, something like what you have seen in your like 10+2 level. Okay, comparing distance between two different points and so on. Okay, you can use that to figure this out. Now, how to figure out the cluster centers? You simply like you have bunch of points in a cluster. Okay, so they are all n-dimensional feature vectors. What you do, you basically take the mean vector of all these things. So something like this. Okay, if there are say n points in a cluster, you simply take the mean vector, which will represent the cluster center. Okay, so K-means is basically a classic example of centroid-based clustering. There are other clustering techniques that you will get to know in the next lecture, maybe. But that is why it is called the centroid-based clustering. That each cluster will be represented by one vector, which is the centroid of all the points in that particular cluster. Okay. All right. Next. So one important thing in K-means, and which we try to minimize, is called K-means loss. Okay. So as you know, in any machine learning algorithm, you need to have an objective function. And our objective, of course, would be to either maximize or minimize that objective function, depending upon the application. So in k-means, our objective would be to minimize the k-means loss value. Okay. So the k-means loss value is defined as this: is essentially the sum of square distance from each point to the associated cluster center. You take a point, say for example xi, then you see in which cluster it belongs. Okay. Then you compute the distance between the cluster centroid and the point, and simply you take the sum of all these values for all the points in the cluster. Okay, that's called k-means loss value. And our primary objective would be to minimize this k-means loss value. How we can cluster the whole thing so that we can minimize this value. That's what we're going to do. Okay. Now, what's the running time of k-means clustering algorithm? So in every iteration, what you do, you first assign the data points to the closure cluster center. Okay, so that you can do in order of k into n time. There are k clusters, okay, and there are n data points. So you have to compute the minimum distance between all the centroids and one particular point. So it's roughly order of k into n time. Okay, and then change the cluster center to the average of its assigned points. How this can be done? This can be done in order of n time. Okay, so in every iteration, this is the total amount of time that you're going to spend in order to do that. And so if you want to run, say for example, m iteration, you simply multiply the whole thing. Okay, and that's how basically you can compute the running time. So a few issues that we have to figure out in k-means. First of all, the value of k. We talked about k-means, all, but k-means requires that you set the value of k a priori, that how many clusters you want to create. Okay. The second is how to stop, whether a fixed number of iteration, partition unchanged, cluster centers do not change, and things like this. Okay. And third and most critical issue is initial cluster centers. Okay, and I'm going to show you an example how things can go wrong if you choose the initial centroids wrongly or badly. Okay, so these three issues kind of the main issues in k-means clustering algorithm. So how to stop? This is kind of mechanical thing. Kind of very rule driven, so I'm not going to spend any time on it, but I'm primarily going to talk about how to choose the good value of k and how to choose the initial cluster centers. So let's talk about how to choose the value of k in k-means. Okay, so yeah, please.
Yeah, like how we will be handling like equal distance values, like while assigning each cluster to an example, like if an example is closest to two clusters, like with an equal distance, like which cluster we should have to assign?
That's a good question. So one way to handle this is that when you see something like this, then you can actually consider the individual points in the clusters. For example, one particular points will have equal distance from say cluster A and cluster B, for instance. Okay. Now what you can do, you can look at the points from cluster A, other points from cluster A, and other points from cluster B, and you can measure the distance, okay, and then take the minimum distance. Okay.
Okay, sir. But this may be like increasing the phi of kn, right? Like complexity.
Yeah, it will of course increase the complexity, but again, this kind of situation may happen very rarely. Right? It can be very rare. Yeah. Okay. Okay. Now let's talk about how we can choose the value of k. One important issue. Okay. So before I start, I simply want to make a very simple comment on it. That the methods that please.
Sir, can we say that the worst time complexity would be k into n squared?
Complexity would be yes. That's k into n, right?
No, sir, k into n square.
K into n square.
Yes, overall computation till the data won't change till the cluster.
But why it is n square?
So like we can say that in each of the iteration the this midpoint of the cluster will be changing, so it will change across all the points.
Okay.
Can we say like this?
So if you look at this slide, I hope you can see my slide, that in every iteration, there are two main components. One is taking order of k into n time, another is taking order of n time. So if you simply add them up, it essentially order of k into n, simply because of the complexity theory's definition and all, right? So are you convinced about that?
Okay, sir.
Okay, and then if you simply run multiple times, like multiple iteration typically, okay, which is basically constant number, so it will be some c into k into n, order of that, which is equivalent to order of k into n. Now k is typically again constant, doesn't depend on the number of data points and so on. So it's basically is very small, which is roughly again translated to order of n complexity. But of course, there are some hidden things in it. For example, I am ignoring the time to compute the distance between 2 points or b dimension and so on and so forth. So those things you can actually factor in, but roughly assuming that those things are very small compared to the number of data points that you want to cluster, so essentially order of n time. Okay.
Yes, yes.
Okay. All right. Okay. Any other question? All right. Okay. So let's talk about how to choose the value of k. And again, this is something that I want to talk, okay? And I would like to tell you very bluntly that there are many things in machine learning, okay? There are many strategies, many things in machine learning. They sometimes work, they sometimes do not work, okay? So this is not only about k-means, this is true for deep learning, SVM, and so on and so forth. So the things that I'm going to talk about, please do not assume that these things are definitive, okay? So these are some suggestions based on the experimental outcome. This may not work or may work. Probably most often it works, but there are other situations where it may not work. So the things that I'm going to talk about now, they are essentially some guidelines. Please do not take it as a definitive things. Okay? Maybe for your data, these things may not work. That is perfectly all right. Okay, you have to probably find out some other ways of handling this whole thing. So that is a small thing that I want to tell you before I get into this. So let's talk about how to choose the value of k. One method that people typically use, and I think is very popular, is the elbow method. Okay. So what is the approach? Your main primary objective would be to figure out a good value of k. You do not know how many clusters you want to create for your data. So what you want to do, you want to figure out what would be a good value of k. So how can I do that? So what you do, you vary k, okay, from 2 to say a very large number, okay? And then for every k, you are going to get a k-means loss value, because for every k you can compute that. So simply plot this whole thing. In x-axis, you have the number of clusters, and in y-axis, you have the corresponding k-means loss value. You simply plot this and see whether you can get an elbow shape thing, okay? And the point where you can see the bending is taking place, okay? You can take that, the value of k at that point would be a good thing to accept. So if you look at this particular diagram, the good value of k could be 3. There's sudden changes in k-means loss value, okay? It's very sharp change. So something like this you can actually do. Now this is called the elbow method because the shape that you're expecting is like elbow, okay? The bending point, and you can take that value. Now, many students actually reported to me that they didn't find anything when they are applying this particular technique on their data. I also myself experienced this particular thing. So again, I'm telling you that this is a guideline. It probably works in some situations, but you should not accept this as a kind of ground truth. Okay, it may fail. Okay. Second is called Shewhart measure. Okay. Again, the key ideas, there are two things, is one called the small within cluster variance and large between cluster variance. So this is kind of the good, like the key idea for good clustering. When you are going to measure the quality of the clusters, okay, you want to look at this two particular thing. Whether the within cluster variance is very small, but the between cluster variance is very, very large. Okay, you want to make the clusters tight, but the different clusters will be far, far apart. That's what you really want to do. And this particular measure will depend on these two factors, factor 1 and factor 2. So, practically it looks like this. So in within cluster measure, what we really want to do, we want to take all the points in individual clusters. Okay, so you want to measure the similarity between or distance between individual pairs of points in individual clusters. Okay, you simply divide this by number of points in the clusters and you get some value Aij. Okay, take all pairs of points in individual clusters and then do it. Now, in between cluster measure, what you want to do, you can take the points from different clusters. For example, you want to measure the between cluster distance between, say, cluster C1 and cluster C2. So you can take the points from cluster C1, cluster C2, then measure their distance and take the minimum distance. That is called BI. And then you can basically normalize this whole thing. Okay, BI minus CI by this and so on and so forth. So this higher the measure, better the clustering is. Okay, that's the main idea in this case. Now let's look at the graphical view of this whole thing. Okay. Now say you vary the value of k in the number of clusters from 2 to say whatever number that you want to create. Okay. And then for every k you can compute the silhouette measures SI. Okay. You can take also the average and so on and so forth. And then you basically plot along the y-axis and x-axis. Along the x-axis you have the number of clusters. Okay. And you can simply take where you can find the peak, because the higher the value, better it is. So you can choose the point where you are going to get the highest value. Okay. Now again, there are other measures. I'm not talking about all this, but again, I'm telling you, repeating the same thing again. This is not a foolproof method. Okay. So all you have to do, you have to basically look at whether you are getting the elbow shape or you are getting this shape and so on and so forth, and then accordingly you can choose it. Okay. Now, this is another important factor in clustering. How to choose the initial cluster centers. Okay, and this is where actually a substantial amount of research went into to figure out what would be a good strategy to set the initial cluster centers. Okay, let me tell you why this is important, and then I will discuss about a particular technique to solve this problem. Now what you do in this case, go back to your random initialization business. Okay, that is a bunch of points. I want to create 3 clusters. Okay, so I'm going to choose 3 initial points randomly from my data without any additional information. Okay, so say I have ended up selecting these 3 points, the purple, red and blue. Okay, you are choosing randomly, so this might quite be a possibility. Now, if you do that, what will happen? Okay. So once you do this, then you do your assignment and recalculation of centroids and so on and so forth. Then you are going to get the clusters something like this. Okay. Something like this you're going to get. So as you know, this is actually very bad clustering. This actually does not identify or uncover the real clusters in the data. Okay, so therefore you know that how you are going to select these initial centroids is going to play a very important role, that what you are going to get finally, and that is why this is a very, very important component in k-means clustering. Okay, so there are other consequences of it, that if you choose these initial centroids badly, then your convergence could be very slow. That means it can take lots of time before you get reasonably good solutions. Again, what you have seen in the previous slide, it converges to suboptimal clustering. Okay, which is basically either of these two is very, very bad. Okay. So the common heuristics that people actually use to tackle this, one that I already mentioned, the random centers. You can randomly choose the centers, okay, from space. You can randomly pick from feature vectors. You can basically choose some points based on the farthest center heuristics, which I'm going to discuss in detail in the next slide. Okay, so that the points are very far apart, initial points. Okay, you can also try out multiple times. Okay, you select k centroids randomly, you run your algorithm, then again you do it, and so on and so forth. You try it multiple times, then see where you are going to get minimum k-means loss value, and then accept it. Okay. Some people also apply some other clustering technique. Okay, very weak, very efficient clustering technique to find out some good centroids, and then you use this centroid into the k-means clustering to figure out what would be the good clustering and so on and so forth. So there are many approaches that people actually proposed. Okay. Now, one of the popular approach, of course, is the farthest center heuristics, which I'm going to discuss in the next slide, and then I will tell you the more kind of the recent technique which can solve this problem. So in farthest center heuristics, what is done is this. The main intuition again is that now if you choose these initial centroids which are very close to each other, then you are going to get very bad clustering. So all you have to do that you have to choose these points in such a way that they are kind of dispersed. Okay, they are coming from the different places in the space. Okay, they are very, very far apart. So that essentially the intuition behind the farthest center heuristics. So what it is? Now first you randomly choose one point. The first point you choose randomly. Okay, and that is your first center. Now for the other k-1 centers, assuming that you want to create k clusters, so other k-1 centers you can actually choose by looking at the distance from all the centers that are already selected. Okay, and taking the points which are the farthest distance apart from the points that you have so far. Okay, that is essentially the idea. Now let's look at this particular example and things will be clearer. Okay. Now say I want to create 3 clusters. Okay, and so I have to basically select 3 cluster centroids from this data. So say I first randomly choose one point. So my first point would be something like this. Okay, there is no choice. Now for the second and third point, I can actually apply the farthest center heuristic. So for the second point, okay, it could be something like this, because this point is farthest distance apart from the purple point. And so I pick this as a second centroid, potential centroid. Okay. Now I have to choose a third centroid. Again, I have to basically take into consideration the existing centroids, the blue and the purple, and then I choose the point which will have the maximum distance from all this. So it will be something like this. Okay. Now if you do this particular technique on this particular data, it seems that this is going to solve the problem that you are actually facing in the previous example that I already have shown you. Okay. But unfortunately, this is not always the case. And I'm going to illustrate. I'm going to take another example to point out that where things can go wrong if you want to apply this particular clusters, this centroid selection technique. Okay, so for this it is good, no doubt. Now that's all right. So the issue with this approach is this. If you look at this, that your data is something like this. Okay. In any real life data, you have a set of outliers, that the data points which are basically noise, or for some reasons that you can basically call them outliers. They do not follow the typical pattern that you expect. And that is pretty common phenomenon in any real life data. Okay, it is nothing artificial. It's actually real. It happens. So say that I have this data in this form, and I have to create 4 clusters from this data. Okay. Now, if we apply the farthest center heuristics, then you are going to get these 4 cluster centroids initially. Okay. Now, what it will do, ultimately, you are going to get one cluster finally centered around the purple box and the other singleton clusters. Of course, this does not give you the natural clusters that you can see in your data. Okay. So that's again, it's a problematic thing. Okay, you should not use this thing. Okay, make sense? If you have any question, please let me know. Okay, all right. So this is the problem with this one of such popular approach. So in order to tackle this, there are many algorithms. Okay, people have actually developed, because k-means is one such important algorithm, and very widely used. Okay, almost in like many applications it is actually used. So many people develop many techniques to tackle this problem. Now, one of the most recent approaches that I'm talking about is called k-means plus. Okay, as the name suggests, this is the increment over the standard k-means. Okay. So the only difference between k-means plus and k-means is the way k-means plus actually initializes the cluster centroid. That's the only difference. The initialization step actually differs. The other steps remains the same exactly as is. There's no difference. Okay. So the approach that it takes is called basically probabilistic approach. Okay, and I'm going to show you how it actually does that. So what it does, it chooses one center randomly from this data. First center you can always choose randomly from the data. Say this is C1. Okay. Now you have to choose k-1 centroids, others k-1 centroids. Okay. So how you can do that? For every point in the data, okay, every point x in the data, you compute dx, some distance x. So dx is the distance of x from the closest center you have already chosen. Okay. So now what you do? You select a data point x as a centroid with a probability value. Okay, and what the probability value would be? It is actually this dx square by sum of this. Okay, the denominator is simply because you have to normalize this because this is a probability distribution, so you have to do that. Okay, so every point you are going to consider, then you compute the distance dx, then you simply select this point with the probability value. You can simply use some random number generator from your Python library or C library or whatever library and see whether this point can be selected with this probability. Okay, and if you satisfy that, you simply accept this one as a potential centroid. Okay, and in this way you can simply do these things until and unless you select k centers. So idea is that, and there is a connection between this one and the farthest center heuristic with a difference. So what is the connection? That the probability value increases. If you look at this, the probability value increases with dx. If dx is high, then probability value is high. That means if the distance from the closest center is very high for a particular point, then that particular point is going to be selected as a cluster center is also very high. So in some sense, it actually mimics the farthest center heuristics. But what is the difference? The difference is that the farthest center heuristic is a deterministic approach. This is always going to select a point which is farthest distance apart from the existing points. No doubt what it is. But in this case, this is a probabilistic approach. Okay, you can probably select that point with more likelihood, but definitely not always the case. Okay. And that little change actually made lots of differences. Now, this seems little unintuitive, okay, but people actually proved these experimentally and theoretically and all. And this particular algorithm works pretty well. Okay. So that's the way this is going to select the all other points as a cluster centroid, and simply you then apply the other steps in a standard k-means clustering algorithm. So let's take a look at this very simple example to illustrate how it actually works. Okay. So on the top, again, I have the main steps for selecting the centroids, and say I have this data, okay, which I want to cluster, and I want to create 3 clusters out of this data. Okay. Now for that, the first cluster I will need to choose randomly because I have no other option. So say this is the first center. This is deterministic, like kind of you can randomly choose one particular point from the data. Okay. Now, what could be the potential? The second centroids. There are so many other points, and which point I can actually choose as the second centroid. Okay. So the most likely second center, and I am emphasizing the word most likely. Okay, because this is a probabilistic approach. Because the probability that this particular point, okay, the second point will be chosen as the second center is very high because the distance is very high. Okay, it's the most likely second center. Now, what will be the most likely third center? So do something like this, because now then you have to compute the distance between the first center and the, say for example, the second center, the red bar, the red line and the black line, and you can see the distance is very high according to the red line. Okay, and so you can basically select this particular point with the probability value. Okay, again, probability value is given by dx squared by sum of this and so on and so forth and so on. And this way, basically, you can proceed and find out what would be the other cluster centers and so on and so forth. Okay. Now, again, I am telling you that this is a probabilistic approach. You have to basically use some kind of random number generator from your library to figure out whether you can accept a particular point with the probability value. Okay. So that is how you can basically use this technique to figure it out. Okay.
Sir,
any question? Yeah, please.
Sir, like while we will be generating one random number and then we will be selecting that point and then we have to see the probability rate. Like,
right.
Yeah, but how much should be that probability? Like, if should we have to accept that X?
So you already have this thing. So if you look at step number 3. Okay.
Yes. So, like if we select some point, like if we get some point like and the probability is 0.001, like should we have to accept that thing or not?
No. That is not. So you compute the probability value from step. So what is the accepted probability? That from step 3 you can compute that what's the probability value. Okay, and then you can use your Python library. Okay, to kind of the way that you can compute the probability values, random number generator, and so on and so forth. And you simply compare these two and say then you can accept the whole thing. The standard implementation which you can basically do.
Sir,
Yep.
sir, let me assume that I have all my data points on a single line. Then how to tackle this problem? Like if I increase the k, then the loss function is reduced.
Can you please repeat again?
Sir, I have all the data points on a single line. Like
Right.
assume that 0, 0, 1, 1, 2, 2, and so on up to 5.
Right.
Like increasing k reduces the loss function. Then how to tackle this problem?
Yeah, so that's actually a good question. In any case, I mean, if you simply increase it, irrespective of whether this lies on the line or not, if you simply increase the number of k, then generally you can see that the loss function is actually going down. This is generally the case. Okay. So there are one suggestion that I actually missed out is that you can vary k from 2 to root over n, where n is the total number of points. That's the maximum limit that you can consider. Okay, not beyond that. And the second again that I'm telling you that you could actually look at this elbow or the silhouette measures and so on and so forth and see whether your data is actually revealing any pattern out of it. Okay. If not, then straight away use your requirement. Okay, that how many clusters you have to create and simply hard code it. Make sense?
Yes, sir.
Yeah. So that's why I initially told you that nobody can guarantee that this is the best clusters that you can get out of particular data. Nobody knows that. Okay, any other question?
So
Yes.
you want to maximize the distance from all the previous centers or only just the previous center?
No, you can basically say, look at this point X. Okay, the point X, right? Now, because you already have say 2 centroids that you selected, you simply compute the distance between all centroids and particular point. Okay, and then you simply take the closest. So in this case, your dx will be the length of the black line, and your probability will depend on that. Because if you want to maximize the minimum distance, essentially you are maximizing the distance between all other points, right? That's the essential idea, isn't it?
Yes, sir. So it should be farthest from first center and second center as well.
Yes. So see, when you say farthest from second center and this one, yeah. So the real objective is something like this, yeah. So if you look at this particular example, it will be clearer. So all you need to do, you need to basically compute the dx, right? Because the probability depends on dx only. Now the dx will depend on, in this case, there are two distances, the red line and the black line, and you have to select the black line. Is it clear or still you are in dilemma?
Yes, sir. Yes.
Yeah. Yeah. Any other question? Okay. All right. So thank you for attending, and see you tomorrow again at 8.
Sir, a small
Yes.
question.
Yes, sure.
Sir, we implied that we have to choose the black line between the red and
Right.
white. Okay.
Right.
So what does choosing the black line mean?
Okay. So assume that you have the first center and second center you already chosen, right? Now we are going to choose the third center. Okay, so that's what I'm going to do in this particular slide. Now every point you can consider, because every point you have to consider whether for this third centroid. So you have to compute distance between the already existing centroids and the point. Okay, so in this case, say I am considering now x, the point x, and I want to compute the probability that this particular point will be selected as a centroid. That's my objective. So in this case, what would be the value of dx? Okay, the dx, the value would be either it could be red line or it could be black line, right? Either of these two possibilities, right?
Yes, sir.
Yeah. Okay. The question is which one I should choose, red line or the black line?
Black line.
Okay, the black line, because simply I want to make it as far as possible from all existing points. Otherwise, what will happen if you simply, for example, choose this, for example, red line, for instance, what can happen is that some point which is very close to first center can be chosen with very high probability because it is very far apart from the second point. That's why you want to basically maximize the minimum distance.
Yes, sir.
So that they are not very close to each other. Okay.
Sir, how did we overcome the problem of outliers with this approach?
Can you repeat again? There is a bit of noise.
How did we overcome the problem of outliers with this approach?
Okay, so see the problem of outliers, there are many approaches you can. So in K-means, or you are talking about in general how you can tackle that?
Yeah, in K-means.
Yeah. So in K-means, you can actually, what you can do, you can run the clustering algorithm and see with multiple different values of K and see the number of points in every cluster that you are getting. You look at the distribution and see whether a particular cluster having very small number of points. Okay, you can set a threshold or something like that and simply discard that. Because what you expect that when a particular point is outlier, so any cluster forming around that particular point will have very small number of points, something like that. But it's always very tricky. Okay, so. Okay, any other question? Okay. Okay, so then we sign off and then we will meet again tomorrow at 8 a.m. in the morning. Okay, so thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.